Hello everyone, my name is Shijing Liu. Today I will present our paper titled Decentralized Structural-RNN for Robot Crowd Navigation with Deep Reinforcement Learning. Let's begin with some introduction. Nowadays, more and more robots are moving from labs and factories and entering people's daily life. When this happens, navigation in crowded places with other dynamic agents becomes an important problem. Here are some examples of applications of crowd navigation, which includes robot companion and autonomous delivery. In this paper, we seek to build a learning framework for robot crowd navigation that allows the robot to perform spatial and temporal reasoning. Next, I will talk about some previous works on robot crowd navigation. One line of work is reaction-based methods, which uses one-step interaction rules to determine the robot action. Examples including ORCA and social force. However, both of these methods suffers from the freezing robot problem, meaning that in a dense crowd, the robot will find that no feasible path exists and therefore freezes in place. Another line of work uses reinforcement learning. For example, in deep V learning, the agent chooses an action based on the state value from a value network. However, deep V learning is typically initialized by ORCA with supervised learning, and therefore it also inherits the freezing robot problem. Also, the dynamics of the humans are assumed to be known and deterministic, which can be unrealistic in real life. In this paper, we present the following contributions. First, we propose a novel deep neural network called Decentralized Structural-RNN, or DSRN, which incorporates spatial and temporal reasoning for robot crowd navigation. Second, we train our DSRN network using model-free RL without any initializations using supervised learning. By doing so, it simplifies the learning pipeline and also avoids the network from converging to a suboptimal policy too early. Third, our model outperforms baseline methods in various challenging navigation settings. We formulate this robot crowd navigation problem as a Markov decision process, or MDP. More specifically, the state ST is the joint state of the robot and all the humans. The action AT is the velocity of the robot. At each time step t, the robot takes an action based on its policy, which takes a current state as an input and outputs the current action AT. And then it transits to a new state ST plus 1 according to its state transition probability. The goal of the robot is to maximize the cumulative return RT, which is defined in the equation. Next, I will talk about the deviation of DSRN from a spatial temporal graph. As a first step, we model the crowd navigation scenario as a spatial temporal graph, or ST graph, as shown in the figure below. In the ST graph, the nodes are the robot and other agents. There are two types of edges. The spatial edges are the vectors pointing from the robot position to each human's position. If we unroll this ST graph along the time axis, the temporal edges is a vector pointing from the robot's position at time t to itself at next time step t plus 1. And then if we convert the ST graph to a factor graph, we can effectively factorize the robot policy function into three smaller factors. They are spatial edge factor, temporal edge factor, and node factor. Here is a picture of our DSRN network architecture. We parameterize the spatial edge factor as a spatial edge RN, which captures the spatial interaction between the humans and the robot. We parameterize the temporal edge factor as temporal edge RN, which captures the dynamics of the robot's own trajectory. Next, the output of the spatial edge RNN and temporal edge RNN are fed into an attention module, which assigns an attention weight to each human. Finally, the node-RNN combines all of the previous features as long as the robot state to determine the robot action and state value. By splitting the complex navigation problem into smaller factors, each RN can learn the parameters of its corresponding factor more effectively. Next, I will move on to the experiments and results. We use two OpenAI gym environments for training and testing. In the first environment, the robot has a limited field of view, or FOV, and this environment simulates the limited sensor range of the robot. The second environment is called group environment, and it simulates the dense crowd. The group environment is used to evaluate whether the algorithm has the freezing robot problem. We train our DSRNN with proximal policy optimization, or PPO, for 10 million time steps. After training, we evaluate the performance of our method with 500 unseen test cases. Then we compare the success, collision, and timeout rates with two baseline methods, ORCA and OM-SARL, in both environments. ORCA and OM-SARL are representatives of reaction-based methods and previous RL-based methods, respectively. As we can see in this figure, the performance of DSRNN is more robust with a decreasing field of view compared with the baselines. In group environments, the timeout rates of ORCA and OM-SARL increases significantly as number of humans increases. This means that both of them have the freezing robot problem, as we shown earlier. In contrast, the timeout rate of DSRNN stays low throughout the time, and therefore is less prone to freezing. Here are two examples of our model's performance in both FOV and group environment. We also successfully transferred the simulated policy into a real-world TurtleBot 2, and this is a video demo. In conclusion, we propose a DSRN network that incorporates spatial and temporal reasoning for robot crowd navigation. We train the DSRN using PPO without any supervised learning or assumptions on agents' dynamics. Our model outperforms baselines in simulation and works well in the real world. Here are the references. Thank you for listening, and I will be happy to take any questions.